fused computer. Good morning and welcome to lesson 23, and the topic for today is flow duration curves. And a flow duration curve is a natural extension of some of the probability estimation modeling we've been doing, although it produces what looks to be the same thing, but the interpretation is quite a bit different. And so we'll go over that briefly in this presentation. And the whole point behind that is to guide any field work or project development or our hydrologic characterization of watershed of interest. So usual dogma here is preparing for water-related field work or project development. Advanced knowledge of site hydrology, including weather, stream, discharge, stream stage, and so on, is vital. Things that matter are things like discharge per square mile of basin area. That's a remarkably important quantification if we are intending to use the basin to supply water. The range of annual precipitation over the basin, pretty much for the same reason, and the percentage of annual basin flow occurring in each month or in a particular time period. These are the kinds of quantifications one would like to make for a basin. A basin could be very large or a very small hydrologic component. We have the added bonus feature that the sites are usually located on streams that do not have operating stream gauges, and so it might be difficult to locate data. And there's two approaches. One is to use a nearby gauge and transpose it. The second one is to use downscaling. In yesterday's presentation, I don't think I actually got to it, but it is in the presentation materials. So I'm going to verify that. So in lesson 22, there we go. So this is just to finish yesterday in lesson 22. We waited for a black projection screen. We, any particular reason why you're not working now? Oh yeah, you're a computer. We demonstrated that we could use R in our earlier tools to produce Pearsonian type fits, and then we examined peak FQ 7.3, discussed the missing intervals and low and high outliers. There's some additional guidelines in Bulletin 17C, which are not directly related to flow duration curves initially, but they make sense. Is that the station record length should be at least 10 years. And here's some of the narrative from the report. And then there were record extension methods that are described. One's called MOVE, which is maintenance of variance extrapolation. I think that's what the acronym means. The other one's transposition. They're really the same thing. The formulas are adjusted slightly to produce different results. We'll briefly look at transposition. And then furthermore, Bulletin 17C mostly is focused on the expected moments algorithm called EMA. And the components of that as applied to the current hydraulic design manual for Texas, and that's just one of 50 states. The three arrows that are here on this slide are largely what the focus of Bulletin 17C was created to do, was to provide a way to use weighted or regional skew values. The accommodating outliers, more or less, we can put the nail in that coffin and consider it done in 17C, and then transposing. We went through this, and here's the transposition. So transposing is actually a very simple idea. It says a discharge at an ungauged watershed can be correlated to the discharge at a gauged watershed, presumably nearby, same hemisphere, same state, same planet, multiplied by the square root of the area ratio between the two gauges. Transposition historically is used more as a spatial tool. So a way to move information to an unknown location. Although it is very much a record extension technique in the Bulletin 17C document. And that returns us to today's presentation. Which handles its bullet item. There's two options for finding data: stream flow values from a nearby gauge site of about the same drainage area size. So that's a transposition approach where the area ratio is 1. Or downscaling from a nearby stage, and that would be the area ratio as in the prior slide. So continuing to use the nearby same size, find the drainage area of the project site, locate a gauge site similar in size. From the list of gauge sites with similar drainage area, identify the ones that have similar topography and climatic zones and the project site, and then just go ahead and make the transposition. There's some important considerations. And those are that the drainage areas are indeed, you're going to have to go in a cage. Excuse me for a minute. All right, the miniature puma is now in his cage, so we can possibly continue undisturbed. The considerations for transposition are that the drainage areas are indeed similar, so those area ratios don't get much different than maybe 3 to 1, but not 10 to 1. That may be unavoidable, and in which case you would simply note that in your analysis. The topography needs to be similar. So using a 100 square mile watershed in central Texas would not be a good comparable for a 100 square mile watershed in North Dakota. I'm making a gross assumption there that the topography of the two is sufficiently different. And by that topography, mountainous, desert, valley, pretty much roughly the same elevation changes and same morphology of the watershed as examined from aerial imagery. The climatic patterns should be similar, so that takes the North Dakota-Texas comparison right there. Soil characteristics should be similar. So taking that 100 square miles and trying to compare it to a watershed in the Kuma Desert in South America the driest place on Earth, would be problematic, because the soil characteristics are going to be vastly different. And land use should be similar. So forested, urban, agricultural, and so on. The length of period of records should be close. Downscaling is a different approach. Operationally, it's pretty much the same, but find the drainage area, the two sites, the comparable site and the project site. Compute the drainage area ratio. Usually take the square root of that ratio, and that's the downscale multiplier. And it too is based on some additional considerations. First is that a small watershed responds differently than a large basin. If nothing else, it doesn't have much storage by virtue of being small. So it's going to convert a lot more input into output, where a large basin, because of potentially quite a bit of hot basin storage by virtue of its size, that conversion process might be quite similar, but the transfer of that conversion to the outlet occurs on a much different time scale. And the differences are listed here. On small watersheds, precipitation tends to generate runoff fairly quickly because there's not much time or area for infiltration. And on large basins, in contrast, the travel distances are longer, the contact area is much greater, there's substantial channel storage and other on-watershed storage, and hence the runoff reaches the outlet slower relative to the input signal than on a small watershed. And often the discharge per unit area is smaller for a large basin. And that's a consideration. So that's really the guidance, to try to keep the area ratios as close to 1 as practical. Now there's going to be instances where that's just not possible, and one would have to do the best they can. Now the record length is important too. We saw that in the Bulletin 17C guidance, in that they recommend 10 records, but Bulletin 17C is specifically targeted for annual peaks. And possibly with shenanigans as software, it could be used for some other time interval, but the labels that it's going to produce in its reports lose meaning at that point. So it can certainly estimate probabilities for different time intervals, but how to interpret them will be up to the human being. We can't have a computer do it for us. So in continuing, drainage area and topographic characteristics are certainly important factors to address when selecting a gauge site to represent an ungauged site. But the length of record needs to also be considered. A larger data set, meaning longer record, is expected to produce more representative results for some of the reasons, such as the longer the period of record, the more likely it is that the stream flow statistics generated will be representative of the long-term flow pattern of the stream in question. Okay, that's a lot of words to say. The longer the record, the more observations there have been that allows high-frequency variability to average out, and we're getting a much better average representation of stream behavior. So using the mean flow record and mean monthly flows based on 61 years of observations would allow much more confidence than values based on 10 years of observations. And we could visit the Bulletin 17C software and demonstrate that to ourselves. We could use the Bear Creek data, for instance. It had 31 records. We could knock out 21 of those and reanalyze it, and we would see those error bars, which were the blue curves on the peak FQ output, they would move farther away from the red fitted curve. When using a shorter period of record, it's likely that the flow values can be misestimated, and that would ultimately lead to errors in determination of design flow. So again, longer record is better. Discharge patterns are more easily detected using a longer record set. The short period record shows annual monthly patterns to be quite a bit more erratic than long period record. So, thus it's advisable to search for the longest period of record possible that also meets the other criteria. Again, good dogma, not always possible. And when it's not possible and there's still a need to do it, you don't give up. You just have to acknowledge that the confidence in your estimate and your design is quite a bit less. And so, okay, skip that. So now we get to the focus of today's lesson, which is the flow duration curve. So, in words, the flow duration curve is a plot that shows the percentage of time that flow in a stream is likely to equal or exceed some specified value of interest. And this information is useful for design of structures on a stream and some other utility. It's useful for policy. It's useful for selling water or scheduling water diversions. So what the flow duration curve shows, either graphically or tabular or functional, is the fraction of time river flow can be expected to exceed a specified flow. So for example, let's specify a flow of 20 cubic feet per second on some stream. Somehow for us that's important. And what we can get from the flow duration curve is what fraction of time will we see that 20 cubic feet per second or greater. And in a mental experiment, that means, if we go out and look at the stream at random every day, for let's suppose 100 days, and at random, so it's not 100 consecutive days, but 100 days in a year. How many of those days will we observe 20 cubic feet per second or greater? So if 80 out of those 100 days we go out and look at the stream and the flow is greater than 20 cubic feet per second, that would be the specification that 20 cubic feet per second has an exceedance probability of 80%. And less than 20 would be 20%. And so what you can gain just from that small statement right there is that 20 cubic feet per second is fairly common on that stream. So if you had a process or need to exploit that 20 cubic feet per second, only 20% of the time would your exploitation process fail. That's what a flow duration curve is attempting to convey. So we can design structures to work well within some range of flows, such as flows that occur between 20 and 80% of the time. And the rest of the time, we don't expect the structure to perform very well. And in flood management, we usually use the 99th percentile. So when we build infrastructure that is subject to flooding, we would like it to function 99 times out of 100. And we accept that there will be a 1% chance in any given year that our structure will fail. And I mean fail by hydrologically fail. Possibly physically fail, but hydrologically fail. And that is a common risk standard that's used throughout the United States, perhaps even the world. So 1 in 100. The basic time unit in flow duration curves greatly affects its appearance. So one could argue that the flood frequency curves that we produced yesterday and the day before are a type of flow duration curve. And that's a fair argument in the context that it's on an annual basis. So the annual biggest flow duration curve is the same thing as what we call a flood frequency curve. That's kind of an important observation, because that observation, at least intellectually, allows us to make the important leap that, well, the analysis techniques and software we've already developed could be cobbled to work for flow duration curves, and indeed they can, and we're going to attempt an example later on in this lesson. So for many studies, the mean daily discharges are used. Nothing particularly special about that, except that that data is probably most available on our national website. Daily discharges give a pretty steep curve, and by steep it means it's steep at the extreme ends. At the low end and at the high end, the curve is somewhat steep. When the mean flow over a long time period is used, such as mean monthly flow, the curve itself is flatter. If we do annual, which is what our flood frequency curves look like, I mean, they kind of look steep, but they're actually quite flat in the whole scheme of things. And the flattening of the curve, very interesting word choice considering the time and history we're all living through. The flattening of the curve is a consequence of averaging of the short-term peaks within the intervening smaller flows during the month. And the extreme values get averaged out more and more as the time period gets larger, such as the flow duration curve based on annual flows along record station. There's a particular picture from a document that's in the reading list that I'm going to go ahead and try to bring to life. And these materials, these have not been uploaded to the server yet, so I will get it there after the lesson. So in the supplemental readings, there's a paper on flow duration curves, and there's a particular figure in it that's important to me. So, well, all of us. So this figure, although not directly addressing this time period thing, is shows the relationship of the daily variability and then the flow duration curve. So here's a hydrograph on some river, and if we look at the time period, 47 to 87, 40-year time period, over that 40-year time period, the hydrograph has this variable behavior. And we observe in the flow duration curve this behavior, in that 50% of the time the discharge is greater than 10. Let's see if I can get some drawing tools on here. Let me open this in a different software tool so I can draw on it. machine. Okay, it refused to do that. We have one more way to do this. And actually, I'm going to clip that and put it into the PowerPoint because it'll get away from that awful looking arithmetic stuff. Insert. Okay, that'll at least save it for the time being. Now I can at least draw on this, which is the whole point. The 50th percentile from the flow duration curve is somewhere around I think I got that right. It's not particularly flat. Okay, that's not bad. It's right about there. And if we look at the hydrograph, that's plausible. That appears to go through what would be the mean of the hydrograph. The relatively rare values, excuse me, not rare, the high discharges, so over 100 units, there's 1, 2, 3, 4, 5, 6, 7. 7 of them pictured here. And they are representing that end of the flow duration curve. Then if we move down to the low ends, let's say, let's pick one. We have a few there, 3, 4, 5, 6, 7, 8, 9, 10. Let's drop it just a touch more. So those spikes at this end, at this 1, 2, 3, 4, 5, 6, 7. The low values are representing this end of the flow duration curve. And it's written as exceedance probability. So observing a stream flow value of 0.1 units, we expect to see a value of 0.1 or greater almost always. And so its exceedance probability is approaching 1. We're at the right end of the curve. A flow value of 100 units or greater, we don't observe those very often, so we're at the left end of the exceedance probability curve. And then the middle part, actually I want to change the color on that too. That behavior is explaining what's left, everything that's left in the band. What the flow duration curve can't capture, it's not designed to, would be this clearly, at least to me, periodic signal in the hydrograph. And I'm not sure if that's the particular long wave periodic signal, but there is one just by looking at it. And that's largely what this whole presentation slide is about. As the time period gets bigger, if we use larger time units, the blue part of the curve gets flatter and flatter, and the influence region of the steep edges gets squished in the probability scale towards each end. If the time unit is really small, a lot of this variable behavior gets in the way, or is captured. So the actual analysis, in most studies, the Weibull plotting position is the probability estimation formula that's used to turn that wiggly hydrograph into exceedance probability estimates. So the daily discharges are ranked for the period of record from largest to smallest, and we get a total of n values. We're going to do an example shortly that I think has about 11,000 values. So chose that example partly because I have a place to go look, see if I got it sort of correct, and partly because it was big. 11,000 is not big in the data science world, but it certainly is too big for doing Excel in a reasonable amount of time. We assigned each discharge value a rank, starting with 1 for the largest and moving up that, and then calculate the empirical exceedance probability as P is 100 times cap M, which is the rank over n plus 1. It's the Weibull plotting position, so we've already done this. And then here's what is produced by these kinds of things. And I have the high flow regime and the low flow regime identified in this picture. And this particular picture is from another source, and the author of that source is trying to show the effect of using a 10-year period of record versus a full period of record. And in using the shorter record length, in this particular example, there's a lot of low flow probability shoved over here to the right. Actually did pretty good in the high flow regime. And that is possibly changes over time. The shape of those upper and lower regions is pretty significant in evaluating and interpreting the stream and basic characteristics. Sounded like somebody just had a disconnection. Lost somebody. No, it's still all for y'all. I apologize. My machine was talking to me. We'll return to the show. So the shape of the curve is significant. In the high flow region, the shape of the curve tells us the type of flood regime that a basin is likely to have. So a very steep curve, which would be high flows for short periods, would be anticipated for a small watershed that responds strongly to rainfall. So think of it as almost a flash flooding. Where in contrast, snowmelt floods, which last several days, or regulation of floods with reservoir storage, would result in a flatter curve near the high flow regime. So this one, I would argue, is not particularly flat. It's kind of steep, because it's flat here as it approaches that, and then it hooks upward rapidly. So this would be a very flashy watershed. So the Alsea River near Tidewater is a watershed that either has rain-caused floods on small watersheds, or is maybe a desert watershed subject to rare but significant flash floods. Now, that particular river happens to be in Oregon, so it's most likely a rain-induced watershed response. The low flow region also gives us some information. It characterizes the ability of the basin to sustain low flows during dry seasons. So that has some importance. That's a lot of importance in water supply. An intermittent stream is going to have periods of zero flow. And so we have no zero flows on this particular stream. But if we had zero flows, as we moved along here, this thing would plummet actually down off this log scale. It would drop very rapidly. Flat curve indicates that flows are sustained throughout the year, and that can be attributed to natural or artificial stream flow regulation. So natural would be groundwater supplying water to the stream, which eventually goes by the gauging station. Artificial would be we have reservoirs in the watershed, and we do scheduled releases to maintain stream flow. It's kind of the whole point of reservoirs. And those are the possible interpretations there. So now let's apply our existing toolkit to these ideas. And we're actually going to look at the North Fork of the Alsea River, Alsea, Oregon. This URL, which just this should be the query that would generate the data set that I'm going to show you. So first we have to download the data, then we're going to have to format it for our tools, and then we'll process and interpret the results. So the tool I'm going to use is the R script that we prepared yesterday for the log Pearson 3. And it didn't have to be the log Pearson, it's just that that gives us the ability to see how this might work in a PeakFQ type tool. So here's what the file looks like when it's first downloaded. It has some usual header information, tells us what site it is, it tells us what's actually being provided. So the parameter is daily mean discharge in cubic feet per second. A means it's been approved for disbursement, and I've added so there's an agency code, a site number, date and time, a couple of other header informations. So the 114506003 is the actual data. And then the last part here is the code, the A, B, C, D, and so on. And then there's a few other fields that are available, but they appear to be empty in this file. I Actually, those look like format codes to me, so it's telling us what each field would look like. So we could take that file, let's just go to the bottom of it. Let's scroll through it, see if there's anything weird in it. And you can see it's relatively long file. I believe it has 11,600 records in it. So we're going to want to format that into something we can use. And so I earlier went ahead and did that. And pretty much what I did was just clipped off all the comment fields and put in some header names. And we're going to use QDay as our important header. And we'll try to read that file in, and then produce a flow duration curve. So the tool I propose using would be our R script from yesterday, which, by the way, is repaired and now runs on the remote website just fine. Actually, this will be good because I can show you what I repaired. So anyway, the only change is this script was added. So when that gets uploaded to the Share Hydro server, it just works because this particular library won't compile on that server for some reason. I tried quite a bit of that. Okay, so we're going to change our input function to input. And the other, let's get rid of that. Get rid of that. Get rid of that. And now we'll just go ahead and run it. Let's save it. We're going to have to make some other changes, but I want to verify that we can load in the file. So now let's see if we successfully, 11,687 observations. And it did not parse them correctly. I wonder why that is. I bet I have a spacing error. So let's go fix the input file slightly. That's what I was afraid of. It's tab delimited, and we're using a very crude read process. So let's see if we can edit that. We'll find and replace. We're going to find tabs, and we're going to replace them with dual white space. Okay, so I'm not going to click that 11,000 times. I'm just making sure that it's picked up the pattern correctly. And did wrap around. And now the test. Okay, so we're good. Let's try that again. So we'll go back to our tool. And we'll attempt to reread it. It still failed. Okay, so during the read we have to identify the separator. My bad. And yes, I could have put commas in. That was actually kind of stupid of me. Okay, so maybe that worked. 9 variables. 2, 3, 4. Not exactly what I wanted, but we now have this variable called QDay isolated from everything else. So we will continue with that. Save that, and we want this to be QDay. Probably should have given the header QP, so then I'd have less to change. And Q day. And then this is no longer an annual exceedance probability. And the recurrence interval doesn't make sense anymore. So let's go ahead and delete that entire part. Save. So we've just done the read. Label. And all I'm really after actually is the plot of the circles. I don't even care if it can model it correctly. So the circle plot right here represents the empirical cumulative frequency distribution. And it also looks to me that we are way at the wrong end. So the flows here are quite a bit lower than on Bear Creek, so we could change this. Let's go to 1/10 of a flow unit to 1,000 steps of a half. That's going to be an awful lot of number. Okay, so we've now modified our discharge, our plotting scale, and the black line is the empirical flow duration curve. The blue line is a model fit that has no meaning in this instance. So now that I would say we have this working, let's modify what gets plotted. So we're going to plot we're going to modify the plot call. So we're going to plot while plotting position versus day. Copy that. That goes here versus the copy that. That goes here. And we'll call this flow duration curve. Okay, so we modified our existing tool, hit that, source it. Good, that's starting to look like a flow duration curve is supposed to. And now if we want to, if for grins we want to put our model in there, then we need to get a lower limit and an upper limit. So we'll go ahead and put lower is equal to the minimum of a y plotting position. No, actually I just plotted the wrong thing. It's going to be the minimum of the flow and the maximum of the flow. Oh, it didn't break. That's cool. Now we can modify that plot call. And naturally, it's not too hard to conclude that if you had to do this a lot, one would simply write a code to specific for the analysis of the river of interest, and then document it and test it, and then be done. Okay, so we are plotting a Weibull. Color should be blue. Type is going to be point, and now type is going to be line. Let's stick with our I think red is what the peak FQ used, and then the observations were, I think that's a legitimate color. Okay, so that's going to be points. Move on. There we go. So the teal colored curve is our flow duration curve for these data based on observations. The red curve is a log Pearson type 3 fit to that data. And so we can infer some things about it, either directly at the curve or using the tool as a function. So our 50th percentile is 10, 50, 100. So our 50th percentile is probably around 100. Let's test that conjecture. So that's the 53 percentile. We can actually also learn something else. We can look at the mean value of Q.dB $QDAY. Let's see what happens if we put 275 in as a 275, the other 275. In this case, 275 is at the 25th percentile. I think this is work on the right edge. So the 30th, so 25th is right here. I'll look at one other value. It's 10 raised to the u hat 117. So one other attempt to try to get the mean. We'll put in 117. Put in 118. Okay, so the mean value of discharge is somewhere between 118 cubic feet per second and 100, which falls in this region right here, as expected. Let's look at the common flows. So the low flows happen a lot, or excuse me, in terms of exceedance. The low values are exceeded a lot more commonly than the high values. So if we put in a value of, put in the minimum, let's see what the minimum is. So the minimum is 12, so let's put in 15. So a discharge value of 15 cubic feet per second is observed, the flows in this river are observed to have 15 cubic feet per second on average any given day, or greater, 94% of the time. So if we were to visit at 100 days randomly spaced out over a time period, over a year, at least a year, we visit 100 times over a year. 94 of those visits will measure a discharge 15 CFS or greater. 6 of those visits, it'll be less than. And if we visit enough, we'll probably narrow in quite nicely into those values. Now these estimates here are actually being taken from the red curve. I'm not directly interpreting the teal values, although there is a way in R to do that. So that is what our flow duration curve looks like. Go ahead and save that with all of my modifications. And I hope you can see that a flow duration curve using our existing tools isn't that hard to build. Now, I have no idea what would happen if I were to take this file and load that into PeakFQ. So I think PeakFQ could read it. And there's 10 minutes of the, well, there's actually 20 minutes of the scheduled time left. And for fun, I want to try that, so that's what I'm going to do. So I need to make it so I can get to it. You see what happens if we put that in PeakFQ. I want to leave this around so we have something to compare it to. So what I think PeakFQ would do is, I think it too would produce its red curve and then have all of its blue curves also. The probabilities would be correct and the discharge would be correct. The meanings of 100 year, 500 year, 1,000 year would be completely ludicrous. The interpretation, but PeakFQ I think can do this analysis. And I seriously have never tried. And so now today seems like a good time. So bear with me as I figure out a convenient way to transfer the files. I think the most convenient for me is going to be to put it on local web server. It's running. I hope it's logged in. Oh, thank heavens. Okay, so it's already logged in. And I think I can drop it here on the index page. Okay, so that's taken care of. We can leave this, and we'll go to the class web page. Student. Actually, let's do it number 1, because I think I have correct script there. Actually, I think it's in number 3. Perfect. So step 1, let's get the data. Now bring this up to full screen. Cool, but that didn't break. Go to the remote. Wait a little bit. There's the data. I don't think I can drag and drop. No, it doesn't work. So I need to download that. So the file should be here. Close that. Push this over here. And let me go to the downloads and we'll put it in the right place. So I'm going to create a folder with the same name. PKFQ seems to work better if you keep everything contained in folders. I'm not sure, it doesn't necessarily work better. It mitigates failures. We'll go ahead and attempt to execute the program. And I am pretentious in thinking this is the first time this has ever been done. But it's possible. Open my computer, navigate to there goes nothing. Error message. Rats. No, it's not quite the right format. Oh, that's a shame. This format on the right side would have to be converted to this format. I think much of the data is actually already there, and I also believe it's possible to download the data in the WattStor format. So that was my mistake. So we actually can't compare them today. What I would have expected to have happen is that the peak FQ would have produced a plot quite similar to the one that we got in our R script. And that concludes today's lesson. And I think tomorrow's the last day. I believe to have grades, I'm going to have some kind of final examination. It's going to be something in the order of one of the quizzes you've already taken. So maybe a 10 or 12 question quiz. I'll program that tonight, and I'll go over it tomorrow, and then you can have, I'm not sure, I think grades have to be on Saturday, so you have to Saturday night to get it done. As a reminder, be sure to upload exercise set 3 and work any of the outstanding lessons or quizzes that the server will allow you. I don't foresee anybody earning less than a vowel in this class, so if you were shooting for vowels, I think you have them. Also, there's a course evaluation, the online thing that the instructional support people, you would have gotten emails on that. Please go ahead and fill that out. Often in the past, I don't really care, but this time I do, because this is a new mode of course presentation, and I'm aware that this particular summer session there were a lot of flaws, but I can use your guys' feedback to correct those flaws. I didn't change the share hydro site during the course, but I figured a better way to make it run more reliably in the future. Reliable in terms of connection, reliable in terms of file management. So I'm aware of that. And if there are no, what's going on, computer? Yeah. If there's no questions, I will go ahead and end for the day, and we'll meet last time tomorrow. And what I intend to do tomorrow is summarize everything into a single short lesson. What we did not get to this session that I had wanted to was water quality aspects, because that's the obvious next step in hydrology, and more of the integration of the HEC HMS output into the swim environment, which water quality would have given us the connection for that. So in the future, I'll take care of those. So have a great day, and I will go ahead and end today's phone call. If there's no questions, so you got like 10 seconds to ask a question, or I'm going to disconnect.
Oh, I have a question. There was one of the lesson, or I guess just like class sets that I did when I wasn't paying attention and selected the wrong button, it doesn't let you retake that. So, like, is that bad if I have like a 0 on a...
I think I'll be able to tell when I go on the server that you tried, and pretty much someone tried.
It was on one of the true-false ones, and so, like, I tried.
I'll say don't worry about that, because there's only 7 people. I'm going to go through the server tools, and it'll tell me that you attempted it. I can tell that. And if you've actually looked at any grading on the server already, you may have seen scores that have, on my computer, they're a yellow-orange background. the numbers associated with that are instructor overrides. And so they usually pretty much they're 100 to their 98s. And so I override what the automatic grading machine scores. I can do that for a false entered instead of a true. So don't worry about it.
Okay. All right. Thank you.
Anything else? Okay, well, very good. Have a great day, everybody, and I'll see you tomorrow. Bye-bye.